Hi, good day. My name is Leke Akinola. Today I'll be talking about my work on the synthesis and the characterization of two-dimensional metal carbides. I've done this work in collaboration with colleagues and professors from the University of Texas at Austin. So in my talk today, I will be introducing Maxins as another class of two-dimensional materials. I'll be talking about the properties that Maxins have, and then I'll be going through my motivations for deriving magnetic metal carbides. I'll be taking chromium carbide as my case study moving forward from there. Then I'll be talking about my exfoliation method in synthesizing chromium carbide. After that, I'll present my results and I'll have some discussion about that, and then I'll give the summary slide. So let's delve right in to introduce Maxins as another class of two-dimensional materials. There is a vast array of two-dimensional materials that are out there, and Maxins is one group of them. Now, two-dimensional materials are interesting because they display a wide variety of electrical properties. They can be insulating, they can be semiconducting, and they can be superconducting as well, and everything in between. Maxins hold a good place in that, depending on the functionalization, as we'll discuss later on, they can range from semiconducting to metallic, and also they have different magnetic properties as well. So here we'll present the periodic table of elements, and we show the place where Maxins hold. In green here you see transition metals, which are one of the elements of the Maxins, and then we have carbon and nitrogen, which is one other major element of Maxins. And when transition metals bond to carbon or to nitrogen, we have MXenes. We can also use the same argument for nitrides like boronitrides or gallium nitride, or for MXenes and germanium and organic materials and transition metal dicotyledons as well, using this periodic table. So where do Maxins come from? Maxins come from the bulk Max crystal structure, where M signifies transition metal, as we've seen earlier. A is a group 13 or group 14 element, which can be gallium or germanium or aluminum. And X is carbon and nitrogen. And when you see it from top-down view, you have this hexagonal structure. So to derive Maxins, all you have to do is to remove the A element in the MX, in the MEX structure, and then you have MX nanosheets that's been derived there. And when you look at it from top down, you have this hexagonal structure that is also similar to what you have in other two-dimensional materials as well. And depending on the functionalization, then you begin to have different interesting properties. Now, functionalization is a organic or natural process that comes from the synthesis of Maxins through exfoliation. And when you exfoliate, you have these T elements, which can be fluorine, oxygen, hydrogen, or hydroxide, that naturally bonds to the chromium and result in a functionalized surface for the Maxin. And based on this functionalization, you begin to see different electronic properties that can be exploited. So Maxins display various electrical properties. The bare Maxins are metallic. The metallic properties decrease with increase in number of MX bond. In this situation, titanium X bonds or chromium carbon bonds in my situation. The nitrides are more metallic than the carbides because the N atoms has more electrons than the C atoms. The surface terminated Maxins are either narrow band gap semiconductors or metals. The band gaps range from 0 to 2 electron volts. They are mostly indirect band gap when they have band gap, and as the tensor strain increases, the band gap gradually decreases, and this indirect band gap that they mostly have can transition to a direct band gap on application of tensor strain or an electric field. They also have other interesting properties from mechanical properties, in that they have high tensile stress capability, like 5122788 gigapascal. They have good thermoelectric properties as well. Semiconductor Maxins show good Seebeck coefficients. they have been predicted to be magnetic as well, like chromium carbide or the chromium nitride are predicted to be ferromagnetic or antiferromagnetic, and they also have good optical properties as well. That has been as they've been tested on. Now let's me walk through my motivation for deriving magnetic metal carbide. The pristine titanium carbide and titanium nitride have been predicted to be half metallic ferromagnets. The chromium carbide and the chromium nitride has also been predicted to have good, interesting ferromagnetic or antiferromagnetic properties as well. One thing that's very unique is that these magnetic properties can be engineered, improved, and band gap tuned based on the chemical functionalization that it's been done to them, and also based on strain engineering. The half metallic energy gap in chromium carbide, for example, is 2.85 electron volts, and so this shows us that it has some stable ferromagnetic properties as predicted in theory. Now, to derive this chromium carbide, let's see some of the procedures and steps that I've used. First is to give a general overview. The general overview is in synthesizing Maxins is to start from the bulk max, do a chemical exfoliation to get an accordion structure, and from the accordion structure do some physical exfoliation to get a few layered nanosheets. Now, the reason the accordion structure is important here is because from experimental work that's been done on other Maxins in the past, the accordion structure is characteristic of a successful Maxin derivation. And so to do this for chromium carbide, I got an hot iron pressed chromium aluminum carbide. The hot iron pressing was done from chromium aluminum carbide, and then this chromium aluminum carbide ceramic chunk was grounded into millimeter dimensions, after which I etched out the aluminum to give chromium carbide, and then I did a chemical delamination with tetraprotyl hydroxide, and then a physical delamination with tape method. Now, to move on with the etching after grinding the chromium aluminum carbide to millimeter dimensions, there are three options I could use. Number one is to use an HF etchant, which is mostly used out there. The problem with that is that the lateral dimensions of the product are not brilliant, and also there are more impurities involved. One other thing is to use ammonium bifluoride. Now this is a good option because the ions in the bifluoride, in the ammonium ions and the fluoride ion, the ammonium ions actually go with help with further intercalation of the sheets. And the third option here is to use fluoride salts and acid, and this fluoride salt and acid method has been shown to actually help with a cleaner, pristine sheets derivation with less impurity. The other thing is that we have better lateral dimensions of the sheets that come from it. So using the third method, I set up my experiment using this chemical equation as shown here, and then I conducted the experiment in a cold environment until the reaction is complete. And after the etch, I washed in hydrochloric acid and to dissolve the precipitate and impurities, and then washed in DI water up until like a pH of 7. And the DI water helps in further the intercalation of flakes. And then for the chemical delamination, use tetraprotyl hydroxide to help with separating and intercalating the sheets further, and then washed and dried the resulting flakes, and then I characterized it. Now let's move on to the major results and discuss about them. So to have something to compare this with, I started with the bulk max chromium aluminum carbide and did the EDX characterization from this. And from here you can see that the aluminum peak is strong, the aluminum signal is strong, and we want to reduce this aluminum signal significantly. This will show us a successful etch. So I started with lithium fluoride with HCl at room temperature, and even though I was able to see the accordion structure begin to show up after 72 hours, and the reaction was completed after 96 hours, one thing that is important to take note of here is that there's a lot of impurities showing up as well after the etch. The other thing is it's a long process. It takes 96 hours for the reaction to be complete, and so we needed something that would be easily realistic and integratable in the industry, and so we needed to reduce this long etch hours significantly, and also find a way to clean up the reaction. There are three variables I try to optimize for. First is the temperature. I realized that the etching reaction is an exothermic reaction, so perhaps doing the reaction in a cold environment will actually help in speeding up the rate of the reaction. There has been work out there that suggests using a increased temperature would help, but this is contrary to what I observed. The other thing is I decided to use sodium fluoride instead of lithium fluoride, and also I decided to switch up some of the reactant concentrations as well. After doing this, I got to a good spot, a sweet spot, and I realized that using HCl plus sodium fluoride at 9 degrees centigrade using the mild method gives me the best reaction product. I was able to reduce my reaction time from 96 hours to 45 hours on the average. Also, I realized that the number of impurities in my products was significantly reduced as well. So this shows the scanning electron microscopic images of using lithium fluoride and sodium fluoride. And one of the things to take home from here is that when you use lithium fluoride, even though the etch is as successful as when you use sodium fluoride, the fluorine peak here is still showing up significantly. And whereas when you use sodium fluoride, the fluorine peak is not as strong as you have in the lithium fluoride compared to the chromium. So that shows that sodium fluoride actually gives us less impurities or less contamination compared to the lithium fluoride option. One other thing that is important to take note of is also how the lateral dimension of the nanosheet actually is 5 times more than the initial method I used, and so this shows us that we can get increased lateral dimensions with reduced with a colder environment for etching, and also with sodium fluoride as our etchant, and also the yield was actually much more than the previous example. One thing, last characterization I did was to do the XRD measurement, and this shows the XRD peaks when you scan the chromium aluminum carbide, the unetched one, and you see peaks showing up characteristic for chromium aluminum carbide. And after the etch, you see the chromium carbide peaks begin to show up at these locations, and this shows us that we've been able to actually etch the chromium aluminum carbide to the chromium carbide within convincing limits. And so after that, I think the next stage will be to do the physical exfoliation of the sheets until we get few layer sheets. And to do this, I dried the product after the etch further in an evaporator, and then use a tape exfoliation method to get the nanosheets. And from there, I was able to see that we were able to get some nanosheet structures. And one thing that is important to note here is that we were convinced that this is a chromium carbide sheet because of the peaks of the chromium and the carbon that's showing up here, even though there is silicon, which is the stage on which, or substrate on which it's placed. The chromium carbide and carbon peaks show that this is a chromium carbide nanosheet. This is also the case for this as well, where you have this mass of nanosheets around. So in summary, we've been able to show that we were able to reduce the bulk of chromium aluminum carbide to chromium carbide. We also have been able to reduce the etch time and quality and increase the quality by better stoichiometry and performing the etch reaction in cold environments. The etch contamination was reduced by using sodium fluoride instead of lithium fluoride and washing in HCl before DI water. The tetrabutyl hydroxide helps in further sheet delamination, and physical explanation hold a lot of promise in separating sheets. Thanks to our collaborators, and nice talking to you.